Thanks very much, Mike. And really what I want to bring to bear here is about 20 years experience in the industry looking at these innovations coming through from research and seeing how much of it actually really got adopted, and then drawing from that some conclusions about directions for the future. And where I want to start with is in the domain of wireless, of the software for the wireless systems. And if you look at the progression there over the last, let's say, 5 to 10 years, there's been a remarkable transformation towards this idea of a programmable network, whereby we have virtualized the functions. We've then introduced the concepts of software-defined networking, network function virtualization in the domain on top of VMs in a in the NetC Mano type of context, and then making it a little bit less cumbersome, a little bit easier, more practical, leveraging the technologies coming from the web scales in the cloud world. We've gone cloud native, or we're starting to go cloud native now, introducing Kubernetes, all aiming towards this idea that in the software domain, at least, that we can do this idea of network slicing, creating a virtual network instances for different applications and providing network as a service upwards. So a highly flexible, scalable type of solution, highly customizable, really economical. That's where the software in telecom networks has gone. What about the hardware? And there's what comes to mind immediately is that song in My Fair Lady, where the two rather misogynistic middle-aged men with plenty more means and more money than actual needs are asking the question, why can't a woman be more like a man? And it was a lampoon of a song, and I sometimes feel that way when people ask the question, why can't hardware be more like the software? And what I want to do is to go back and look at the fundamentals, see what has and has not been achieved over the last 10, 20 years, and point, therefore, in directions where we can go in the future as to how to achieve a higher level of flexibility and adaptability on the hardware side of things. So let's first look then at the drivers. Why is it we want more flexibility in the hardware and on the wireless side, particularly on the infrastructure, the RF and the baseband? Well, on the baseband, we'd like to have greater waveform flexibility to be able to handle all of those new schemes that Maria was talking about in the distributed MIMO, a massive MIMO world, and then the various collaborative schemes that we have there. On the RF side, we want to be able to exploit a wide range of carrier frequencies, different bands, whatever we can grab a hold of to aggregate spectrum together to actually create and support larger bandwidths. And we want to be able to handle the huge diversity of the deployment scenarios that we're dealing with now. You look at where a typical small cell base station can end up in. Is it inside a suburban area supporting smartphone users, or is it in the middle of a factory floor supporting robotic communications? Again, huge diversity there. So, ideally we would love to have a much more flexible hardware. But at the same time, there are a number of anchors that we're dealing with, pulling us back and holding us there. We've limited those same limited spectral resources. When we have spectrum, we want to be as efficient as possible in our usage of it. We want to minimize power consumption. We want to maximize the number of devices with the same silicon. So we have things called standards, and this is one of the key characteristics of wireless communications, is those well-defined standards between the terminals and the infrastructure. And that sets markers, and it sets down the limitations of how far and how flexible we can get. The other one, which crops up in this world of cellular communications, is the need to support mobility. You look at the difference between a cellular air interface and, let's say, Wi-Fi. It's hugely more complex, and a lot of that is about being able to support the fact that your users move around a lot. Some of them move at high speed, and being able to support that requires a high degree of complexity in the protocols and the signaling that we have. These are all challenges which hold us back. But I want to dive into a little bit more detail there, particularly on the RF side, because as well as some of those anchors there, those anchors end up basically defining how far we can go. And you look at what we have achieved over the last 20 years. There's been, certainly in the academic community, there's been a lot of research into areas around software-defined radio, SDR. Then the next big buzzword was cognitive radio. We've had in the RF domain, agile RF. But really the things that actually succeeded were driven by very specific needs. So the self-optimizing networks for small cell networks where you have too many base stations to manually configure. You have VRAN splits because you want to scale up your baseband software. You have things like CBRS in the US where you're accessing spectrum at 3.5 gigahertz on a shared basis. So you have to be a little bit more adaptive in terms of the way you manage your RF there. These are the kind of things that really took off, whereas the more broader, expansive visions were actually held back. And if you dive into the detail, you'll find that this comes back to the basic physics of what we're dealing with here. And what I'm going to do is take you through 3 different elements on the RF hardware side and just show you how little room we have for maneuver and how, when you try and increase the flexibility, you run into trouble. So, as I said earlier, once you have spectrum, you really want to try and pack things in, and that has led to some extremely stringent requirements on the front-end filters that we've had. Classic example being the FDD and TDD bands in 2.6 gigahertz for 4G. The two are really right close up together, and as a result, the transmit filters for both systems had to have really sharp roll-off. If you want sharp roll-off in filters, that applies high-quality resonators and filter structures. If you want high-quality filters, then with low losses, then you have to move back to some fairly old-fashioned 30-year-old technology like coaxial filters, where you have air as your dielectric, extremely low loss, and then aluminium then as your conductor, again, low losses. Now, if you want to introduce tunability into that, that's when the wheels start to fall off the wagon. Because to introduce tunability, the typical approach was to insert a tunable component into a structure like a coaxial filter. And to get maximum range or variation in your behavior, you had to put it in where the electric fields were at their most intense. Now think about what you're doing. You're putting a tunable, often nonlinear, variable component into where you have most of your energy. And immediately that led to significant losses. And your Q factor starts to drop dramatically, and you're no longer able to meet stringent requirements. And this has been a tension that has been really dogging this whole space for multiple years. It's a real challenge to try and deal with this. Another example of how the physics tie us down is in the area of antenna technology. So again, tight frequency reuse, let's say in the spatial domain this time, that means you want tight beams. Tight beams means you need high gain. High gain implies you need a large aperture you illuminate a large aperture, and the bigger the aperture you can illuminate in your antenna structure, the tighter your beam gets. And the way we've done this traditionally to get those large apertures is to create an antenna array. So you don't have just one element, you have multiple elements. Now, the thing here is the design of those antenna arrays has a very, very tight connection with the operating frequency. So you want your elements to be spaced at a certain number of wavelengths apart, and therefore if you want something like frequency agility to capture all of those frequency bands, you immediately have a problem because your physical structure here is confining you to particular choices of frequencies just by the very physical design of things. So, again, another constraint. The third one is in the area of power. And one of the big approaches that has been used over the last number of decades to try and improve the agility of our wireless hardware has been to try and eliminate the RF hardware altogether by moving the digital interface from analog to digital as close as possible to the antenna. And, this is a core idea behind a lot of software-defined radio approaches. The issue there is as soon as you move into the digital domain, you have quantization and you have time sampling. And you compare that against what you can do with analog processing. In analog processing, you're in continuous time and you have a much higher degree of precision effectively in your variables. And as a result, you've got a much more efficient, from a power perspective, a much more efficient structure for actually manipulating and processing signals. So the analog domain is very difficult to design in. It introduces noise, interference, all kinds of problems that are difficult to handle, but it is efficient from a power point of view. And that has been always one of the things that has dogged more software-defined approaches. Okay, so I've listed a set of bad news stories here for the last 3 slides. Are we dead in the water? Well, no, not quite. The actuality of it is that if you actually embrace the reality of the physics that you've got behind it and really take that on board, there are always ways around this problem. And this is where I've had a great time working with research teams over the last, a decade or so, is finding those ways of rethinking the problem and then having breakthroughs in terms of getting the kind of agility that we're looking for. So when it comes to antenna arrays, the key thing here to remember is it's not actually arrays that you need to shape a beam. Yeah, that's one way of doing it. You illuminate or excite the medium at a number of distinct points. But really, what you have at the end of the day on a tower is a particular surface area, an aperture. And that's what you really need to play with in terms of your structures to shape the beam in the way that you want, but not to lock yourself down to the actual physics of a particular wavelength. In terms of filters, one of the approaches that we've found that has worked extremely well is to move away from components, tunable components, but to look at tunable media. So what we've been looking at inside Bell Labs has been looking at materials with good loss characteristics, but who, in their bulk characteristic, have ways that can be tuned to have different properties in the RF domain. And what we've done is we've looked at areas such as electrochromatic materials. The other one that we have is dielectrophoretic materials to find and create tunable solutions that don't act on the overall field and the overall device, rather than on a single point inside the device where the electric fields are at their highest. So to try and get to bulk tunability. Again, on the power problem, one possible way forward here, and it's a challenging one, would be to look again at the world of analog computing paradigms, so as to try and combine that flexibility of digital with the efficiency of the analog world. So there are approaches to deal with all of these, but you have to work with the physics, not against it, to achieve the aims of what you're trying to get at. Okay, I want to spend another couple of minutes now looking a little bit at the baseband processing. I'll move a little bit away from the hardware and just look a little bit at a few trends of the baseband processing as far as agility is concerned. And because there's a particular story here I want to pick up on. And if you look at the world of baseband processing, one of the trends that has become very apparent is that we have quite a wide variety of hardware paradigms now in our baseband solutions. Whereas, let's say 10 years ago, you're looking at ASIC or a bit of DSP. Now you've got FPGA, graphic processing units, DSP, CPUs, a whole lot to a full range. And that arises really to better targeting of the hardware infrastructure at a given, for a better matching of the hardware solution to the particular type of processing that you have. So, inside a processing change, we have a huge variety of processes, whether it be equalization, simple detection, decoding, high-level protocols, etc. And you have to pick the right type of hardware structure to be able to deal with it. Now, the interesting one here is the machine learning one in the middle, and it's the only one without an acronym for a good reason, that real-time inference down at the baseband processing side is a pretty new area, so we haven't quite got a good acronym for it yet. But the idea of real-time inference engines is quite an exciting new space, and there are a couple of reasons for that. But let me first talk about how it's likely to develop over the next couple of years. At the moment, we're starting off with, let me just check again. Yeah, sorry. Yeah, so We're starting off whereby at different points in the receiver in particular, we're going to introduce machine learning algorithms and solutions. And that's going to gradually over in time encompass the entirety of the receive chain. That's likely to happen over the next 5 to 10 years, or at least bigger and bigger portions of the chain. In the longer term, the interesting question is, what if we apply the machine learning problem to both the transmit and the receive side? Now that implies some level of negotiation between the two as you go through the machine learning mechanisms to converge on the correct baseband solution. That's kind of the long-term aim where the industry may end up heading towards. It certainly would be a radical change. I suspect it will take quite some time for us to get there to that level of vision. Certainly it's something that may appear in the world of 6G. But the interesting question is, why would we go to that bother? And then there you have to come back and see what the value drivers are for this at the end of the day. And fundamentally, you can see them there at the bottom. The first one is this idea of being able to deploy a solution to multiple different scenarios with a single product. So you will allow the machine learning to adapt to the scenario into which you deploy. That implies as well, though, from a development standpoint, the way that we design and develop these individual components inside the transmitter and the receiver will look very different. So we end up with a generalized structure that learns in the field, so we don't actually necessarily design to optimize a priori. So we have a very simplified development cycle. Then when we get it out there into the field, then we have something that adapts to the particular situation you're in. And ultimately, really what we're aiming for is to be actual to deliver the performance that the end user is actually requiring. But the bottom line here is that when we introduce machine learning, it will be driven by needs in terms of what we need to see in the field. And that's one of the other fundamental messages I want to give through here. When we come back to that question, why can't wireless hardware be more like software? The real answer is, why should it be? And once you have the answer to that question, you can go back and really make the decisions as where you have to put the effort in to get the flexibility that you want, whether it be in the baseband with machine learning or in various parts of the RF front-end chains up front. And that's the challenge that we face, to try and match that need with the physics and with the economics. Bring those three together and you get the sweet spot for increased flexibility in the systems that we deploy in the future. Okay, thank you very much.